Hello everyone, welcome to the week in review. So this is for week number 1. I'm going to try to give brief little reviews like this that summarize what we did in the week, but very quickly. So the first thing we talked about is that this class is about LTI systems. And we talked a little bit about what this is. And what we did is we showed that all LTI systems can be represented as single derivative ordinary differential equations. And in matrix vector form, this looks like this. X dot is equal to AX plus BD. And let's give a quick example so that we remember what this means. So suppose that we have something that looks like Q triple dot, just to make it fancy, plus 4Q double dot minus 3P double dot plus 2Q minus P dot plus 2P is equal to U. U is going to be the input. And also we have a system of equations for P triple dot minus 2P double dot plus Q double dot plus Q dot minus P dot plus 2P minus 3Q is equal to 0. So this is a system with variables P and Q and third order derivatives, and we need to convert it into a simple form like this. Now there's many ways to do this conversion, and they're all more or less the same, and they're all exactly equivalent in terms of what the system's behavior will be. As we discussed in class, we have to keep in mind what's a representation issue and what's a physical property of the system, like stability, etc. So let's go about it just like we did in class. So let's let x1 equal. So before we get to that, a good question for you, and you can pause this and try to answer it before I give you the answer is. Sorry about that. Is what is the state of the system? Okay, so if you want, you can pause it, but I'll give you the answer. The answer is that the state is 6-dimensional, and the reason is that we need to know Q, Q dot, Q double dot, P dot, P double dot in order to propagate the system of differential equations that I've given above. So we should expect a representation x dot equals AX plus BU, where A is a 6x6 matrix. And let's see if that happens. And X would be a 6-dimensional vector. So let's see how we're going to do this. Let's let x1 equal Q double dot, x2 equal Q dot, x3 equal Q, x4 equal P double dot, x5 equal P dot, and x6 equal to P. And so now I need to write the equations above. So note that this means that x1 dot is equal to Q triple dot, x2 dot is equal to Q double dot, or rather x1 dot, x3 dot is equal to Q dot, or just x2. x2 dot is equal to x1. x4 dot is equal to P triple dot. x5 dot is equal to P double dot, or just x4. And x6 dot is equal to P dot, or just x5. So now we basically can just look at this differential equation and rewrite it in terms of x's. Let me try to do that with that going off the screen. So the first one is going to look like x1 dot, and I'll actually move everything over to the right as well, and just leave x1 dot on the left. So this is going to equal minus 4q double dot, which is equal to minus 4x1 plus 3p double dot, which is going to be plus 3x4 minus 2x3 minus plus x5 minus 2x6 plus u. And then the second equation is going to be x4 dot is equal to 2p double dot, which is just 2 times x4, minus q double dot, which is x1, minus q dot, which is x2, plus p dot, which is x5, minus 2p, which is x6, plus 3q, which is x3, and this equals 0. So note that now we have equations for x1 dot, x2 dot, here's x1 dot, x2 dot, x3 dot, x4 dot, x5, and x6, all in terms of x1, 2, 3, 4, 5, 6. So we can now write down our matrix. So we've got x1 dot, x2 dot, x3 dot, x4 dot, x5 dot, x6 dot is equal to x1 dot is equal to minus 4x1, 0x2, minus 2x3, plus 3x4, plus 1x5, minus 2x6. X2 dot is just equal to x1. X3 dot is equal to x2. X4 dot is again this complicated one, so we've got x4 dot is equal to minus 1x1, minus 1x2, 3x3, 2x4, 1x5, and minus 2x6. x5 dot is equal to x4. And x6 dot is equal to x5. So this is our matrix. But what about the u's? So the u, which is sitting right here, only comes into the equation for x1 dot. So we have 1, 0, 0, 0, 0, 0 times u, which means finally that we've got our representation x dot is equal to ax plus bu. So this is our a, and this is our b, and you're going to get some practice with this on the problem set which is posted. So what else did we talk about? The second topic was stability, and we looked at stability for the simple scalar system x dot is equal to ax, and we said that if the real part of a is greater than 0, then it's unstable. If the real part of a is equal to 0, it's in this in-between where it's not going to go to 0 and it's not going to explode, and we call this marginally or neutrally stable. And if the real part of a is less than 0, then we call this stable. And then a slightly more complicated thing that we got into was in the context of looking at x dot is equal to ax, we started saying, well, what if we change coordinates? So what if instead of this point here being represented in this coordinate system, I change coordinates to this coordinate system, and in this case, instead of going to the right by 3 on the blue and up 3, you could go to the right by 1 on the red and up 4. And that describes the same point, just in a different coordinate system. And what we were discussing is that different coordinate systems cannot change anything about the system. This is just a question of representation. So let's give a little example of this. So let's consider the setting where I have x dot is equal to ax. This is a 2x2 system where A is equal to the matrix 1, 1, 1, 1. Okay, and I'm going to, so this means that, x1 dot is equal to x1 plus x2, and x2 dot is the same thing. x2 dot is equal to x1 plus x2. But now let's change coordinates. So let me define z1 to equal x1 plus x2, and for just normalization reasons, I'm going to scale it down by a factor of square root of 2, and z2 and z2 to be x1 plus x2 scaled down by square root of 2. So now I'd like to say, what is z dot equal? z1 dot, z2 dot is some matrix times z1, z2. So this is a simple enough problem that we can just compute it. So z1 dot is equal to, this is just the time derivative of addition. Derivative is linear, so we distribute it, so it's equal to minus x1 dot plus x2 dot. And if I plug in what x1 plus x2, what x1 dot and x2 dot are, I actually get that these cancel. So it's minus x1 plus x2 plus x1 plus x2, which is just 0. So z1 dot is equal to 0. What about z2 dot? z2 dot is the derivative of x1 plus x2, so it's just x1 dot plus x2 dot divided by square root of 2. And plugging in what x1 dot and x2 dot are from over here, I get that this is equal to 2 times x1 plus x2 divided by root 2. But now I want to express this back in terms of z. But we see that z2 is equal to x1 plus x2 over square root of 2, which is what I have sitting here. So this means that I have the equation z2 dot is equal to twice times z2. So in other words, I have my representation z1, z2. So z1 dot is equal to 0 times z1 plus 0 times z2. z2 dot is equal to 0 times z1 plus 2 times z2. So let's compare this to x1 dot, x2 dot, which is equal to 1, 1, 1, 1, x1, x2. So what I'm saying is that these two systems, even though the matrices A, this matrix A and this matrix, let's call this A and let's call this A hat, look very different. Let's give X credit for being first. So this A and the Z matrix A hat, they actually represent the same system. So let's see more generally the transformation that we did. So what we wrote was Z1 was equal to minus x1 plus x2 divided by root 2. And Z2 was equal to x1 plus x2 divided by root 2. So one way to write this is in matrix vector form. Z1, Z2 is equal to the matrix minus 1, 1, 1, 1 times x. So in other words, Z is equal to t times x, where t is equal to the matrix 1 over root 2 minus 1, 1, 1, 1. So let's try to recompute the time dynamics just in terms of this equation. So z dot is equal to t x dot. X dot is equal to ax, so we can plug that back in. So I get that z dot is equal to t times a times x. But now I want to convert this back into something in terms of z. So if z is equal to tx, I know that x is equal to t inverse z. So therefore, z dot is equal to t a t inverse times z. So let's do these calculations. If t is equal to 1 over square root of 2 of minus 1, 1, 1, 1, then you can check, say by hand or by MATLAB, that t inverse is actually going to be the same thing. 1 over square root of 2 minus 1, 1, 1, 1. And now let's look at this calculation. T a t inverse is going to be, I'm going to collect the two 1 over square root of 2's and get 1 over 2 times minus 1, 1, 1, 1 times the matrix A, 1, 1, 1, 1, minus 1, 1, 1. And this equals, well, you can check, but you can check that this is going to be exactly the matrix that we got for C. So the key point is that if we have a coordinate system and a system of equations, x dot equals ax, if we let t be any invertible matrix, then z is equal to tx defines a new coordinate system. It has to be invertible. New coordinates. And therefore, we get the new equation that represents exactly the same system, just perceived differently. Z dot is equal to TA T inverse times Z. And the final thing that we did in class last time, I think we're up to 4, is we showed that A and TA T inverse have the same eigenvalues for any choice of t, as long as t must be invertible. If it's not invertible, this expression won't even make sense. So we're going to pick that up in class starting this week.